All right, so in this lesson, we're going to look at, so this is chapter 11, all right? And we're going to look at permutations and combinations and the binomial theorem. All right, so we call this perms and coms. Outcome P1, P2, P3, P4, and that's what we're doing. Okay, so first thing we're going to look at is the fundamental counting principle. Basically, let's look at the first question and we'll kind of talk about what it's about. So let's say you're going out for dinner and you can choose one of three salads, Greek Caesar pasta, and one of three entrees, so a curry entree, hamburger, or sushi from a menu. So how many possible combo meals of one salad and one entree can you order? So we can make a list of all the possible meals. And if you want to do this for real, I believe Applebee's has a kind of like pick your own option, right? So you can, for like 20 bucks, they've got a bunch of different options for you, and 30 bucks. So you can order a couple of different, choose from a couple of different apps, choose from a couple of different entrees, and then you get a dessert or something like that. So for this case, we'll just simplify it to salad and an entree. So if we have, so let's say we choose Greek salad. So I'll put a G for Greek. And then I choose the curry as my choice. Or I could have a Greek salad and a hamburger, or a Greek salad and sushi. What if I chose a Caesar salad? So Caesar salad, I could choose either the curry, I could choose the Caesar, or with that I can choose the hamburger. And if I choose the Caesar, I can also choose the sushi. Caesar salad. Now I could also, if I chose a pasta salad, I never really understood why a pasta salad is a salad, because it's got no vegetables in it, really. It's all just pasta, right? I don't like pasta salad. I don't like pasta salad. Okay, but some people do. All right, so pasta salad, let's say we choose a curry, or we could choose a hamburger, or we could choose sushi. So how many different possibilities do we have here? Are there any other combination? Are there any other ways that I can organize what I'm going to order? Are the other possibilities? No, right? So there's 9 possible meals that we could choose, or that we could have. 9 different ways that we can arrange this. So this would be a pain if we had to do this, right? And if we were given 25 options for salad and 13 options for an entree. So it could get really too much work all of a sudden. And what if we threw in dessert as an option? So we have a better way to figure out how many different possibilities there are. This is what's known as the fundamental counting principle. All right, so if one task can be performed in A different ways, and another task can be in B different ways, then both tasks can be performed in A times B ways. So, for example, if there's 7 possible salads, 9 possible entrees, and 5 possible desserts, we simply can multiply all of those together and get that there's 315 possible meals. So it would take a long time to name all 315 meals, right? So that's a little impractical. So let's try it with this. So we've got license plates. So how many possible license plates are possible in Manitoba? So we have 6 spots that we fill in. The first 3 are letters, and the last 3 are digits, right? So it's okay to have a license plate that's like A, A and 1, 1, 1. So repetitions are allowed, right? So how many different choices do we have for this first spot? How many letters in the alphabet? 26. How many, so I have the same thing here, right? And 26 here. Now how many digits can we choose from?
10.
So 10, you've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 10. So we have 10 different choices for that here. So if we multiply that all together, what do we end up getting? 1, 7, 5, 7, 6, 0, 0, 0. So that's 17,576,000. Okay?
How many possible phone numbers?
All right. So how many ways can a store manager hire for 3 positions given 12 candidates? So now let's say you have 12 people apply for a job and you've got 3 different positions to fill. So what are the possibilities for this first hire? So you've got how many people to choose from? 12. Now for the second position, how many people are left now? You've already hired one of them here, right? So we've got 11 left. And then how many do we have available for our third spot? 10. Why is there 10 here? Because?
Somebody already took the second one.
Yeah. So you've already got 2 positions filled, so you've got 10 candidates left. All right. 1,320. Right. Okay. All right, so let's have a look at the next section here. Okay. This is what I spend the most time in the morning thinking of what to do. I think a lot of us do. So how many outfits can you order if you have 4 choices of pants, 5 shirts, and 6 pairs of socks? So for me, it's usually like, what am I wearing in the morning, right? Kind of stick to the same types of outfits generally, right? Okay, whatever, I'll stop. So how many different pants do we have? We have 4. How many different shirts do we have? 5. And how many different socks do we have? 6. So multiply, oh, you guys can't even see that. Sorry.
That's all good.
All right, so you've got 4 different pants, 5 shirts, and 6 socks. So how many different ways can you arrange these? Multiply these together and you get 120. Okay. And then finally, for this fundamental counting principle, how many 3-digit numbers can you make using the digits 1, 2, 3, 4, and 5 if repetition is allowed? So when we say repetition is allowed, then that means I could have a number like 1, 1, 1, okay? So I could have something like 1, 1, 1 or 1, 1, 2, for instance, okay? So how many different numbers do I have to choose from for this first? So I've got 5 and then 5 to choose from and then 5 to choose from. So if I multiply all those together, I get 125 different arrangements. Okay, so now if repetition is not allowed, so that means that each of these digits have to be different. So I cannot have 1, 1, 1 or 1, 1, 2, but I could have something like 5, 3, 2 or 4, 3, 1. But these digits cannot repeat. They have to be different. So how many do I have to choose from for this first digit? 5. Okay, because it could either be 1, 2, 3, 4, 5. Now if I've used one of them, how many do I have left to choose from for the second spot? 4. And then how many left for this third spot? 3. Okay? And the order in here doesn't matter, right? So if I were to write the 5 and the 4 and the 3 here, I'm still going to come out with 60 different arrangements if repetition is not allowed. Okay? So that's it for the fundamental counting principle. Let's have a look at factorial notation next. Now, this is by far the most exciting topic in math. You've got exclamation marks everywhere. How can it not be exciting, right? Okay, so where factorial notation, so we're looking at a question similar to this. 6 people must be arranged in a row. How many different ways can this be done? Now, do you notice where we had this? You've got 5 times 4 times 3. Okay, this is where factorial notation comes in handy. So let's go back to this question. Sorry, I'm jumping around. If I have 6 people that must be arranged in a row, how many different ways can this be done? So these are the different spots, right? 1, 2, 3, 4, 5, 6 different spots. And that's how we're arranging the people. There's 6 that can fit in here, 5 left, 4 left, 3 left, 2 left, and 1 left for that last spot. So we multiply all those numbers together, right? And we get 720. Now with factorial notation, you can very quickly write all of this out with a 6 and an exclamation mark. So the exclamation mark is read as the word factorial. So 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. So 7 times 6 times 5 times 4 times 3 times 2 times 1. So what does that equal? 5,040. Now, some of you may be wondering, oh, that's going to be a pain in the butt to enter into my calculator all the time, right? Okay, now, someone has developed a nice little button, and oh boy, where could I find this button? Every calculator is going to have a little bit of a different kind of location to it. In this one here, I'm going to have to remember how to actually access it. What calculator do you guys have? You have the TI-83? This is the TI-85 from back in the day when I was in university. So it's a bit retro for you. Someone have one that I can just steal? Oh, I got one over there. Okay, bear with me while I go find it. Okay. All right, so let's press the math button. And is it in here? Let's go. I probably should have figured this out before, hey? Yeah. I can't remember. Where is it? Do-do-do-do-do. Do-do-do. Okay, I'm going to hit pause and I'm going to find it. Okay, I found it, and we're all kind of looking on it on our own calculators because our calculators are a little different. So what we're going to do is we're going to press math if you've got the TI-83, and then you're going to go over to where it says probability right here, and then if you notice it's number 4. Okay? Some of you might have to press the shift button to find it on your calculator, so don't look just at the buttons. Look at like over here in the kind of like where, you know, above the numbers, it might be somewhere there, like see how you have to access tan inverse using shift. All right, so there's our exclamation mark. That's our factorial. And the way I use it is I put the number in front of it that I want. So I have to go 7 factorial, and then I hit enter, and I get 5040. So that's a much quicker way to figure it out. So 4 factorial, 4 factorial is 24. And 18 factorial, 18 factorial, whoops, wrong one. It's ginormous, right? Okay, so it's 6.40 times 10 to the 15. All right. It's 18 times 17 times 16 times 15, all the way down to 1. All right. So now we're going to look at how to use it in a more general way and how we can actually use it when we're solving for something. One thing you need to know, the definition of 0 factorial is actually equal to 1, okay? And this is a definition. It's not based on a proof. They needed some way to show, they needed like a, just think of it as a placeholder, okay? All right. Now, so let's do a couple of these your turn questions. And then I'm going to get you to try a couple of these on your own. So if I have 11 factorial over 9 factorial, basically we know that this is 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I just wasted a whole bunch of time writing all of them out, right? What do you know about this here? 9, what about this part right here? This is 9 factorial. So if I have 9 factorial down here, I can cancel this out with all of those. So this is 11 times 10, which is 110. Fun, hey? That's exciting. I think that's exciting stuff. Okay, now here, this n factorial. So n factorial is n times the previous number, which is n minus 1, times the previous number, which is n minus 2. I can keep going n minus 3, n minus 4, all the way down to 1, right? But what I have here is I can just write n minus 2 there, factorial, and then that's going to take care of those numbers in the denominator. So you see how we end up with similar factorials? You want to kind of expand it until you've got a similar factorial in the numerator, denominator, and then they cancel out. So this is now n times n minus 1, which is, you could leave it like that, or you could write n squared minus n. Okay? So have a look at these. I want you guys to try these questions, or you could hit pause and then come back, and then I'll show you the answers to these, okay? Sound good? Okay. Okay, so we're back. Let's look at B. So B, you've got 5 factorial over 7 factorial. You can expand this 7 factorial so that it's 7 times 6 times 5 factorial. And then you have here these 5 factorials reduce, and then you end up with 1 over 7 times 6, which is 1 over 42. And for D, if we look at D here, we can expand this n plus 1 factorial so that it's n plus 1 times the previous number, which is n factorial. And then we've got an n factorial here, so those two cancel, and we end up with excuse me, n plus 1. All right. Now, number 2, it says prove. So notice here, whenever you're proving, remember from when we were proving identities, we had left side, right-hand side. So work independently on the left-hand side, work independently on the right-hand side, and go from there. So 5 times 4 times 3 factorial minus 3 factorial. Now what I'm going to do here is I'm going to factor out this 3 factorial, and it's going to be, I don't even really know if I need to do that. I can just solve it. I think I'm just having a little bit of fun here. So I end up with 3 factorial times 19, 20 minus 1. And I can figure this out, which is 6 times 19. And I think the reason why I did this in my head, why I was thinking this route, is what do you notice right here? And what do you notice right here? Whoa! Those two are the same. So, oh, see, factorial, how exciting. They are the same Okay, I know, I'm not funny. I know, I'm sorry, I'm not funny. So that's 114, and this actually also works out to 114. Basically, we need to make the statement that the left-hand side is equal to the right-hand side. Okay? So, cool, no?
Yes, no.
Yeah, fun. Okay. Now, solving this guy, what are we solving it for? N. Solve for n. Okay, so let's expand this until we get, so n times n minus 1, n minus 2 factorial, and that cancels with this one down here, right? So the whole time that's equal to 30. Now I've got n times n minus 1 equals 30. Have that in brackets. So basically I'm looking for 2 consecutive numbers that multiply and give me 30. So if I could figure it out that it's 6 and 5, I can say that those are my options here, right? So it's going to have something to do with that. But let's actually go through and solve it. N squared minus n minus 30 equals 0. Now let's factor this. So n minus 6 and then n plus 5. Now it's a good idea that I actually went through and solved it and didn't just rely on my guess, right? Because what happens here? I get n is equal to positive 6 and n is equal to negative 5. Now, factorial is not defined for negative numbers, so I reject this. And then my solution is n equals 6. All right? Okay, now your life is more fulfilled and has a lot more excitement in it. Okay, we're going to end this one, and the next video is going to be permutations, but it's still the same lesson.